Okay, let's dive into what is, no joke, one of the most revolutionary ideas in modern cryptography. We're talking about a technology that could completely flip the script on how we think about data privacy and security.
I mean, it sounds like a total paradox, right? How can a service analyze your data without ever seeing it? It's like asking a chef to taste a dish while it's still locked in a safe. But that exact problem, that's the puzzle cryptographers have been chipping away at for decades. And for the longest time, it really did seem impossible.
All right, so here's how we're going to crack this thing open. First, we'll look at the core problem. Then we'll get into the so-called Holy Grail solution. We'll see how it comes in different flavors, talk about the massive breakthrough that made it all happen, and finally, check out some of the real-world magic it's already making possible.
So first up, let's talk about this unseen computation problem. You know, it's this dilemma we all face pretty much every day. We want all these amazing services, cloud storage, AI assistants, you name it, and to get them, we have to hand over our data. But the second we do that, there's a risk, right? Our privacy is on the line. We want the utility, but we don't want to expose the raw information.
So the big question is, can we have our cake and eat it too? Can we get all that incredible processing power from the cloud, but keep our data under lock and key totally private? Is it even possible to let someone use your data without actually letting them see it?
Well, it turns out the answer is yes. And it comes from something that people in the field have called the holy grail of cryptography. It's called homomorphic encryption. Now, I know that sounds like a mouthful, but the core idea is actually super elegant and, honestly, pretty mind-blowing. Basically, it's a special type of encryption that lets you, or anyone else, do math and run programs on data while it's still completely scrambled up and secure. So a cloud provider can process your information, but to them, it just looks like a bunch of random nonsense. They never, ever see the actual raw data.
Just think about what that means for a second. You can hand your data over to a third party you don't necessarily trust, like a public cloud server, and they can do complex work for you. They take in encrypted gibberish, they run their programs, and they hand you back a different piece of encrypted gibberish, which is the result, all without ever knowing what they were working on.
There's a great analogy for this. Imagine you have some valuable jewels you want a jeweler to work on, but you don't trust them. So you put the jewels in a special locked box with built-in gloves. You send this locked box to the jeweler. They can stick their hands in the gloves and manipulate the jewels inside the box, but they can't open the box to touch or steal them. When they're done, they send the whole locked box back to you. Only you have the key to open it and get your newly designed jewelry. The work gets done, but your valuables were never exposed.
Okay, but this encryption magic isn't just one thing. It's not an all-or-nothing deal. It actually comes in a few different flavors, kind of like a spectrum of power where each level can do different things.
So on one end of the spectrum, you have what's called partially homomorphic encryption. Think of it like a calculator that can only add numbers. It can add all day long, but that's it. Then you've got to step up, somewhat homomorphic encryption. This one can do both addition and multiplication, but only for a limited number of steps before it kind of runs out of steam. And then you have the holy grail we mentioned, fully homomorphic encryption, or FHE. This is the whole shebang. It's like having a full-blown computer that can run any program you want for as long as you want, all on encrypted data.
But getting to that final all-powerful version, man, that was an absolute epic journey for researchers. This wasn't something that just popped up overnight. We're talking about a long, hard quest that spanned decades. So get this, the concept was first proposed way back in 1978, but then nothing. For over 30 years, it was this long, frustrating wait. Researchers made some progress with those partial schemes, but the full solution, that dream of a programmable computer for encrypted data, it just stayed out of reach. People started to wonder if it was even possible. And then, boom. In 2009, a researcher named Craig Gentry had a breakthrough that changed everything. Let that sink in for a minute. Over 30 years from when the problem was first laid out to the first real workable solution. That huge gap really tells you just how ridiculously hard this problem was. It was a true grand challenge for computer science. So what was Gentry's big secret? Well, the major roadblock was something you can think of as noise. Every time you perform a calculation on the encrypted data, it adds a tiny bit of mathematical noise. Do enough calculations, and the noise builds up so much that the final result is just garbage. Gentry's genius move was a technique he called bootstrapping. It's basically a clever way to refresh the encrypted data, to clean out all that noise so you can keep on computing. And that was the key. That's what unlocked the door to unlimited computation. Okay, so we've covered the what and the how. Now for the really exciting part, the so what. What can we actually do with this incredible privacy magic out in the real world?
Well, one of the biggest and most obvious applications is making cloud computing way more secure. We all use the cloud for everything, but let's be honest, there's always been that nagging trust issue, especially with really sensitive data.
With this tech, you can send your data to the cloud and tell it what to do, all with total confidence. The cloud provider never, ever needs your decryption key. And here's the kicker. Even if a hacker compromises the server while it's processing your data, all they're going to find is a bunch of useless, encrypted gobbledygook. It's a total game changer for security.
But this goes way beyond just cloud storage. Think about a field like healthcare, where data is ultra-sensitive and privacy isn't just a feature, it's a legal and ethical requirement. The potential here is absolutely revolutionary.
Just imagine researchers being able to analyze medical data from millions of patients across the globe to find new patterns in diseases, but without ever decrypting a single person's private health record. This tech could let us build incredibly powerful predictive models to fight cancer or heart disease, all while guaranteeing patient privacy. It could tear down the data sharing walls that have slowed down medical progress for decades. And that really is the powerful question this technology leaves us with, isn't it? For so long, we've been told we have to make a choice. You can have progress and innovation, or you can have privacy, but not both. Homomorphic encryption says, hey, maybe you can have both. What kind of future could we build if privacy was no longer the barrier to collaboration and discovery? It's a question that's moving from science fiction into a very, very real possibility.